It's my pleasure to present you the first speaker of the second part of the session is Emilio Benfenati. Emilio is actually working at the Istituto Mario Negri. It's the head of the Laboratory of Environmental Chemistry and Toxicology. He previously worked at the Stanford University in California in the US, and he coordinated a number of EU-funded projects, many of them on modeling and QSARs, and indeed today he will guide us to understand. I'm sure that you will try to make us understanding QSAR and computational tools. Emilio, the floor is yours.
Okay, thank you for the organizer for the nice presentation and introduction. Indeed, when we talk about QSAR computational tools, we start from a very solid background because this refers in particular to, for instance, a couple of Nobel Prizes which have been assigned in the last one in 2013 for because they took the experiments, the chemical experiment into cyberspace, but even before in '98, there was another one related to computational chemistry. So speaking about chemistry and cyberspace, actually the matter is even broader because a few years ago there was a paper published in the New York Times with this title, "All Science is Computer Science." So if you can just imagine not only our life, but in particular our life as a scientist with our computer, even now, but also in our laboratory, that would be impossible. So this is the key message. Coming back to the chemistry, Thomas already anticipated me. All of us are aware that millions and millions of data, even the following talk will speak more in detail about this, will be available. So how to address, how to imagine, to explore, to reason about all this data without a computer. So the in silico methods are a kind, in my opinion, a kind of glue, a way to integrate multiple evidences. So I'm not saying that in silico incorporate everything. Of course, it's not a matter of, okay, the leadership has to be chemistry or biology or toxicology. It is important that through the computer methods, we have the possibility to establish connections that otherwise are impossible to be imagined. So there are a number of reasons to use QSAR. These are the main one. We will see other later on, but definitely innovation. This is what I just mentioned. And that would be sufficient. The fact that nowadays we are speaking about computer science like a kind of language to connect the different scientific fields. The time for experiments, consider for instance that it took 2-3 weeks for us to predict 4 million substances, the toxicity point of 4 million substances. The number of laboratories. Here in Italy, Federchimica make a survey at the beginning of each, and they discovered that in Italy there are not sufficient laboratory, in vivo laboratory using animals to take care to produce data as required by research. So many Italian companies have to ask India or out of Europe to produce the data. The cost, Thomas already explained this, of course, the ethical issue, use of animals, prioritization, so EFSA, ECA, all the agencies, they have to deal with a huge number of chemicals, but the resources are limited, so we should start from, and for instance, the German UBA asked us to develop a software for prioritization for the PBT assessment. On the other side, there is industry. So also industry should be proactive, not to synthesize and then check and test. But before the synthesis, to anticipate some possible issues. So this is, if you wish, even more is smarter. You can anticipate some of the issues Thomas mentioned at the point of the in vitro, but in this case you don't have even to synthesize the substance, and you can simply work on libraries, as I said, of millions of hypothetical structures. So QSAR basically means that the quantitative structure activity is a kind of a link between the toxicity biology and the chemical entity. And in between, the dialogue is established through the function, the algorithm, the rule. So we have these three main pillars. In silico methods actually refer to a broader set of instruments. So when we talk about in silico methods, this reminds me a little bit of the story of Dr. Jekyll and Mr. Hyde, but refer to chemical. The point, is it possible to separate the bad part, to identify the bad component in a chemical compound? That would be very, very useful, of course, to distinguish what is bad and what is good within a chemical structure. And the QSAR, this is what it's trying to do. So we start from molecular structures, actually not only one. Let's imagine a series, here a matrix of chemical number 1, 2, 3, many substances, and for each substance, one descriptor to thousands of descriptors. And the point is to establish a link between this series of values and your output, the toxicity or whatever. You get a value, you have to compare the predicted and experimental value, and necessarily, this is fundamental, you have to validate the model. And the previous slide was a kind of classical approach in the case of quantitative methods, but the second main kind of model in silico models which refer to fragments. So even starting from human expert, a list of fragments identified by human experts, they identified decades ago that epoxide, the nitroso groups, and so on, are many cases genotoxic. And so there are expert systems which have been developed based on this, but also software can mimic this kind of data mining. Within a couple of projects, Antares first and then Kaleidos, we checked the validity of a number of models. So if you Google Antares or Kaleidos and QSAR, here there are hundreds of models listed with their link, and also we try to evaluate the result, the performance, using, in the case of Kaleidos, the chemicals that industry registered. So these are the experimental data according to industry, and the prediction using a number of models. And this acronym, AD stands for applicability domain, is a kind of jargon, sorry, means the modern models can evaluate if a chemical is more or less inside the so-called applicability domain. So if the prediction is reliable or not, because there's a kind of background, because the model has already seen a number of similar compounds. We will see in a moment a little bit more in detail. And so these are the results. The results are quite good, in particular if you take into account the applicability domain. And then periodically we implement within Vega the best models. Of course, this will not be possible in the case of commercial programs like CD at Topcat, but the other one was these models, CSAR, Pytox 3, are already within Vega. We're in touch with tests developed by the US EPA. Another important point is the consensus. If you integrate multiple models, many cases you improve the results. But this is not always so nice, and there are problems. For instance, in the case of carcinogenicity, also checking the data from industry registered for each. Apparently, accuracy is very high. Well, we're speaking about a complex project. Also, in the case of DevTox, accuracy apparently is very high using this model, but you have to consider that in this case, most of the chemicals are non-toxic. If we consider the toxic substances, there's a number of false negative errors, chemicals which are not correctly identified as toxic. And so if you look at the Matthew coefficient correlation index, you see the value is low. And so there are problems. Why? This depends on the endpoint, because some of the endpoints, carcinogenicity, DevTox, reprotox, of course, these are very complex situations, and it's not just one single phenomenon, toxicological phenomenon. And the other main issue that usually we face is the lack of data. So QSAR a kind of statistical model. If you do not have values, this is a problem. So we implemented within Vega a number of software. Vega is still available in collaboration with US EPA, FERA, a number of people, number of projects. So, for instance, SERAI, one of the also we're active within ToxBank. We will continue with UTox risk, so we will add the logos here. And if you download, you have this kind of possibility for multiple models depending on the property that you wish. But the model, they do not simply make a prediction. So you will have an evaluation. So in this case, the target of the prediction was valproic acid, which has the two chains of 3 and 3 atoms. So this is a similar compound, and you can see the software makes the prediction also on the similar compound. So you can see the experimental value, the predicted value on the similar compounds, and you can measure the uncertainty and the reliability in a global quantitative way, and also in details if something goes wrong, if you have some strange fragment and so on. So this provides you also a possibility to evaluate the uncertainty. I refer, for instance, to the question previously done by Professor Galli. Read-across has been already introduced. The main issue for read-across, I think, is that in most of the cases it is done by the human experts, so it may be subjective. There have been a number of papers describing this. So for this reason, we implemented a specific software for read-across called ToxRead, also is freely available. And this software, the idea is to provide at the center of the target compound a series of similar compounds. Similar compounds are the circles, and the reasons, so rules for toxicity or lack of toxicity, which are the triangles. So if you click on the substances, you see some are, maybe this is toxic, this is more similar to the other one, depending on the size. And if you click on the rules, you can identify what possibly can be a reason of concern, and also you have here the statistics, how many chemicals, what is the prevalence of toxic or non-toxic compound. So, as a conclusion, the computational models are a way to help you, to help us as experts to evaluate the toxicity for risk assessment of a substance. So why they help us? They help us in two ways, through navigating through the different data, and also reasoning. And there are, attention, software addressing one issue or another one. So maybe there are software which maybe explain you in a better way why a certain chemical can be toxic, or other models which are more powerful in the prediction. Consider the issue of consensus. If you combine different models, you have better results, but you lose the interpretability. So there's no conflict between the human and the computer. It's not a kind of black box. And you should use, we recommend there are multiple models, and you should take advantage of each of them, integrating then taking advantage of reliability, which is specifically identified by each model for each substance. And within this kind of evaluation, you should always keep into account that at the basis there are experimental data with their uncertainty, and making the assessment of the predictivity, you should always remember what is the uncertainty and variability of the experimental value at the basis. Thank you for your attention.
So in line with computational tool, you finished up exactly at the time that you have the tone on the phone. Are there any questions from the audience for Emilio? No clarification question, so you have one. Sorry.
Just a quick one, Emilio. I really liked your focus on the reliability of the predictions, and that really being a critical part. And that was brought up by some of the other speakers, as well as the validation of these new approaches. So, in this regard, do you feel like there are some special opportunities where the reliability of prediction can be used, throughout the other areas, in addition to its application to the QSAR kinds of approaches?
Yeah, we are addressing this kind of issue, for instance, within a working group coordinated by EFSA, Kazim, and other members are here. Indeed, the idea is to integrate in silico, in vitro, omics, epidemiology, why not, all this. What is, I think, what is nice in the case of in silico methods, what you have seen is that it has already into its DNA the mathematical terms. So this facilitates a lot the point that you have a prediction, you have uncertainty, and this is split depending on the different components. It may be for chemical reason, for toxicological uncertainty, or for the poor model. All these components are clearly identified. So this facilitates the possibility to integrate with the experimental values, which maybe in several cases they do not think about in vivo reproducibility for carcinogenicity. It's not so easy.
Very good. Well, thank you very much.